Good morning, everybody, and welcome to the CEIA Maths tutorials. Today we've got Mark Murphy. I'm going to hand you over to Mark, who will take geometry of the line.
Good morning, everyone. My name is Mark Murphy. I own my own company. I'm a consultant structural engineer. I specialize in bridges and also I do some fish passes as well. That's what you see on the screen at the moment. So effectively what I do is I graduated back in 96, a long time ago. And I go around the country inspecting bridges initially for local authorities to assess the condition of the bridges and to see if they're fit for purpose and if they can carry the loading that they're meant to carry, and also if any works are required. So what I maybe want to show you this morning is just give you an introduction into engineering, and maybe some of you are more interested in, if you are, ask some questions through the Q&A, and maybe at the break or at the end of the presentation, and I can give you more information about becoming an engineer. So maybe I'll just show you some of the recent projects that we undertook. I just have it over here, 192. So this is a bridge in Tipperary, and as you can see, it doesn't look in brilliant condition. You've got 3 or 4 steel beams, and you've got timber, old logs, and that's one thing. You go around the country, you see a lot of different forms of bridges and different types of construction. But this bridge was in particularly poor condition. You can see, the parapet here, the wall that protects vehicles from over the side was completely cracked. So that was a big issue. I just get rid of this. So we decided that the best thing to do here was to get rid of the bridge altogether and put in a new bridge. So you can see here, look, that's us beginning to demolish the bridge, take it apart. So it always looks very messy when you're actually on site. And we actually found that the ground conditions were so poor here that we needed to put in concrete piles. Now, effectively, what piles are is we core down with these steel cases, and we went down about 20 meters with these, and we filled them in with reinforcement bars here, as you can see, and concrete. And that forms the structure on which we placed the deck. So, this is the deck then. We brought in some precast beams. I'll talk to you about precast beams again later, actually, during the course of coordinate geometry, because actually this week, on Thursday, I got a phone call from site, and I was asked to do coordinate geometry of the line. People always say, do you use maths in the real world? Well, I did on Thursday, so I'll show you that. So that's the deck being poured. And then, you put on some waterproofing, spray it onto the deck, and then this would be the finished job. So a bridge up to modern standards that could take on the required loading. This is a very rural location in North Tipperary. So again, that's looking over the bridge. Not quite complete, but nearly there. Another job maybe was 192. Okay. This is an interesting job. I got a phone call at 3 o'clock back in November 2020 from the lads on the M8 motorway, which is the Cork to Portlaoise, and goes on to Dublin motorway. And this truck went on fire, and it just landed on the bridge. So I was called to do an inspection of the bridge. Now, we couldn't do an inspection of the bridge until they cleared the fire. Now, that's Cork County Fire Brigade and City Fire Brigade. It took them about 6 hours to put the fire get the fire under control. And as you can see here, it was actually on its way to Tesco, and it was carrying lots of meat, pre-packed meat, lamb, in fact. The smell was appalling. It was absolutely terrible. Combined rubber, chemicals, and meat. So eventually we got onto the bridge, and we did look at the bridge, and you can see the damage that it caused to the surfacing. So we took we actually closed the road. The garage wanted to keep it open, but I deemed that it wasn't safe, and we closed it, and they came along and they repaired that road. Another job, maybe 150. I'm just giving you a flavour of what I do, as an engineer. This is a bridge in Meath. Again, it's a really famous bridge up in Kells. It's 13 spans, and we found a lot of issues with it. I'll show you here and see. But it wasn't in good condition. It needed a lot of work. You can probably see there that there's, it's undermined. There's no support on that. So what we did, we came along, we did a lot of repointing work. So I can show you some of it there. The finished job always looks nicer. So we put in grout bags, and we grouted the piers and the foundations to make sure that the bridge was stable. Carried out extensive repointing work on the bridge, which again looks a bit grey at the moment, but then this would be the finished job. That's what the bridge looks like when it's finished. So it's a lot of restoration work. So we're taking old structures and trying to maintain them. And obviously you can see here, the best thing I can say, someone can say to me is, what did you do? I can't see any work being done. That's what we want. We want to leave the bridge as it was, and trying to maintain it. Maybe one other job, 1, 3, 2. So again, this is a bridge in North Tipperary, a very rural location again, but you can see what happened there, right? That's one of the walls holding the arch. So maybe that's a better photograph. So you can see in a right mess, you'd ask yourself, how is that even standing, you know? What actually happens, it actually arches across and creates this new force lines. But anyway, we came along and you can see not in good condition at all. And some engineers in the past would have knocked it and put in a new bridge altogether. But in this case, we felt it was worth saving. And so, you know, we propped it and we rebuilt the walls. And this is what it looks like when it's finished, you know, well, nearly finished. So we would have restored the arch. We got a photograph of it here. That's from the upstream side. So again, we put in this rock armor as well to protect the riverbanks. And also we look after the fish. That looks a mess, but that's exactly what the fish want. You know, the water levels are very low here, but so we look after the fish and the bridges. So again, this is the finished job. So that's just giving you a flavor of what I do as an engineer. And as I say, using maths, absolutely, I use it on a daily basis, and I can give you a concrete example later on. But if any of you have further questions on becoming an engineer, or you know what it involves a lot of traveling, which is great. So you're not stuck in a desk. You know, maybe I'd say 2 days a week, 1 to 2 days, 2 days a week. I'd say on average, I'm in the office doing calculations, contract documents, and you know, carrying out load assessments or doing structural design. But the other 3 days would be out inspecting bridges, or then when jobs are on site, you know, looking at the jobs to make sure that the contractors are carrying out the work as per the drawings, and also addressing any issues that arise on site. And invariably, you do have problems. So if you like problem solving, if you like challenges, and you like solving problems on the spot, and then, you know, a career in structural engineering or civil engineering, you know, could be the career for you. Okay. So I just have to change over my screen out to the iPad, and so new share. Hopefully this works. Okay, it does. Okay, so today's topic is coordinate geometry of the line. Probably one of the easier subjects to do in the Leaving Cert, honours maths paper. I see about 75% of you have done coordinate geometry before, and about 25% obviously haven't, right? So the way I do my course anyways, I go a lot into the theory and understanding, because I think if you understand a topic, then you know you don't need to go over every single past paper for the past 20 years, because you can actually understand it. And for example, look, I'm not a maths teacher. I don't do maths on a daily basis, like, you know, for exams or anything like that. I use it in engineering, absolutely. But what I do to test myself every year is I pick up last year's paper, and I just sat down this morning and see could I, you know, do it. And I did quite easily, because I understand the coordinate geometry line. There's only 7 topics, 7 kind of things you need to know. If you know those 7, then any question they throw at you, you know, can be solved, you know. So what I planned this morning is for the first half, we'll go until about, you know, 11:15, that kind of way. I'm just going to go through the basics and the theory behind coordinate geometry line, and then at the second half we'll do some examples, right? So for some of you, what I'm going to do to start here is going to be so, I don't want to say boring, but let's say easy, okay? But there's a reason I'm going through it very slowly, because a lot of people, like if I asked you, coordinate geometry line is easy, isn't it? And I ask you, what is coordinate geometry? People may not be able to explain it. And as an engineer, by the way, I hate long, wordy descriptions, so I'll be keeping them to a minimum. So look, I'll start straight away, and let's draw a graph. Let's make sure I'm on the right one. Okay. So this is just, we draw a line here. We call that the y-axis. We draw another line here. We call that the x-axis. No, we just randomly pick a point, right? I'll change colors just to keep it interesting for you as well. So we just pick a point here, okay? We call it the point A. Okay, so that's a point in space. And let's give it the coordinates A, B. Now, what does that mean? I'll give you the description first of all. Don't worry, I keep these to a minimum. It says position AB is defined as the intersection of a vertical line through A. So let's draw a vertical line through A. Let's change color again. Let's draw a vertical line through A. That's a vertical line through A. on the x-axis, which is this, and a horizontal line through B on the x-axis. So let's draw a horizontal line. Okay, that is a horizontal line. So what they're saying is this is A and this is B. But what does that actually mean, right? It actually means this, right? So you're coming along this distance, which is a distance of A, and you're going up this distance, which and that distance is B. So in other words, you're going along A and up B, right? That's all that says. So that's the definition, of the position AB. That's pretty much it. So let's go to more kind of, I'll give you an example. So let's draw another. That's your y-axis, your x-axis. Let's draw two lines. The first line I draw here, right? I'll draw through. We call that the line y equals x. And that goes through the origin there, right? Which is 0, 0. Okay. So we call that the origin. And what if we had another line? I give it a different color. And we call this the line, let's draw it first. So that's y is equal to 3x minus 2. Okay. So let's looking at the red line first of all, right? It's saying for any equation in x and y, the points where x, y has values for x and y that satisfy the equation, describe a line on the graph. I hate all that, right? I give you my interpretation, which is a bit better. What this line y is equal to x is saying is that if you come along here any distance, let's say 1, 2, 3, right? And let's go 1, 2, 3 and that, right? What that's saying is that for anywhere along this red line, okay, the y coordinate and the x coordinate are the same. So for example, if we come up here 2 and we go across here, it's 2 as well. So points in that line would be obviously 0, 0 is a point, 1, 1 is a point. And if you went along this way, 555, well then the corresponding y coordinate would be 5, 5, 5. In other words, all these points, this one, this one, this one, they all satisfy that equation where the y coordinate equals the x coordinate. That's all that's saying, right? Now, the purple line there, y equals 3x minus 2, is exactly the same. So it's saying for, let's say, at the point at x is equal to 1, what's y equal to? Well, then y is equal to 3 times 1 minus 2, which is 1, right? Okay. Makes sense, doesn't it? Okay. Now, that's showing something graphically, okay? If we wrote them out here, like y is equal to x, and b is y is equal to 3x minus 2. Now, they cross at a point there. Actually, the way I drew it is wrong here, right? But they meet at a point there, okay? Now, the point they meet at, we can find out graphically what it is by just drawing the lines correctly. Now, I didn't draw the line y equals 3x minus 2 perfectly, so it's not going to be, so you can just bear with me on this. Actually, that's 1 there, right? That's 2, that's 3, 4, 5. It doesn't matter, right? So that's the point 1 there. This is the corresponding 1, 2, 3, 4. Again, this doesn't matter. It's not important. So there's two ways. We could draw the lines perfectly, and where they cross, we know what it is, okay? Or we can do it by simultaneous equations. So we can just substitute y equals x into the second one and rewrite b as y equals x. So we just say x equals 3x minus 2. You solve that and you get that minus 2x equals minus 2. X is equal to 1. And then filling that back into the first one, you get y is equal to 1. So where they meet is at the point 1, 1. So down here, we solved it using simultaneous equations. And up here, we solved it graphically. Now, the story about this coordinate geometry line is there was a guy called Descartes, right? Short story here. He came up with the idea that lines can represent equations in a book called La Géométrie. He invented the Cartesian coordinate system, and that's this, right? This is the Cartesian coordinate system. For the first time, algebra, which is this, all the numbers here, right? And the geometry, which is the visual representation, were forged together. It was revolutionary at the time, right? No one had ever done it. He made both easier to understand. So you can, like, I mean, it's like down here, we solved it through algebra. And up here we solved it just by drawing it out, okay? Now, he wasn't a fan of overexertion, and he certainly wasn't an early riser, this guy Descartes, okay? And in 1649, he moved to Sweden to be the personal tutor of Queen Christina, who was an early bird. And she woke at 5 a.m. every morning and, expected him to do likewise. And he didn't last too long anyway. He contracted pneumonia and he died soon after. So that's the story of Descartes. Now, one thing that always confused me when I was doing my leaving cert was XY and X1, Y1. I'm going to write down something here. I'm going to use the whole page to do it, just to make something very clear to you, okay? You have X and Y. It comes up a lot. And in other places, you'll see X1, Y1, right? Or you can see X4, Y4, okay? Now, this is important. X and Y, when they're in that format, are described as unknowns. We don't know what they are. We're trying to solve for them, right? If you see, so they could be any number, okay? Whereas if you see that in this format, X1, Y1, or X4, Y4, right? They're known values. Now, I go over that again. So in some, you see some formulas, Y minus Y1 is equal to, X over X, whatever, and that's the slope of a line. If you see X and Y, they're unknown, we don't know what they are. They could be anything, okay? But if you see X1 and Y1, they're just representing numbers, definite numbers that we know. In other words, there could be X1, Y1 could be 2, 3, all right, or it could be whatever, 452 and 6, right? That's important. I think that's just something to know. You don't find in many books, but in general, X, Y unknown, X1, Y1, or 8, when it's got that subscript, then it's a known value, okay? So we go on to the first topic, and the first topic is slope of a line. So number one, slope of a line. Again, I don't like definitions, but I'll read out the definition here. But again, by doing examples, they become clear. The gradient, or the slope of a straight line, measures its slope, i.e. its steepness, in relation to the x-axis, i.e. the amount that y increases for every unit of x. So that's flat. That's got much of a slope, right? But the more that the y value increases, so let's say this is the coordinate, so the coordinate is quite low there, it's 0, okay? And as the y value increases, the slope becomes steeper. That's all that's saying. So you could do the big long wordy thing, whereas you can just understand, yeah, that's a steep slope, that's a small slope, right? So that might have a high value of m, and that's a low value of n is the slope, right? So let's just draw it out. It's y-axis, and that's your x-axis. Okay, now let's just randomly pick 2 points. Let's say here's A. That's point A, and this is the point B. Now, we'll give them, let's call this x2, y2. Okay, and we'll call A x1, y1. Okay, so let's draw a line between them. I'll try and get it between the 2 points, not so easy. Okay, not too bad. I'll just make the points bigger. So that's A, and that's B. Okay, now, so we just have 2 points, and we're going to try and find the slope between them, okay? So what do we know? Let's remember at the very start about dropping the lines down and going up to horizontal. So let's go down here with a line, and let's go down here with a line. So then we know that this is the point x1, and we know that this is the point x2. Actually, I'll change color there, right, just to make it clear. So that's the point x1, and that's the point x2. Now, similarly, we can do it the other way. Let's call this y1, and this is, let's write it out here, y2. Okay, now let's call this angle theta. We can call it whatever we want, but for this case, we call it theta. So that's the angle that line, this line, and we call the line L, right? It doesn't really matter. We call the line L. So what do we have? What do we know? We're trying to get the slope, and the slope of the straight line measures its steepness in relation to the x-axis, i.e. the amount of y increases for every unit of x. So how much does y increase for every unit of x? So let's just complete this. What you notice here is we have a triangle, okay? Now let's call this Q. That distance there is Q. Doesn't matter, we could call it whatever we want. Let's call this height here P. So we're just going to define the slope here, right? A slope is equal to, we call it M, right? We could call it anything, but everyone knows slope is M in the books, right? So we'll stay with that. So again, going by the definition, it says if the amount that y increases for every unit of x. So in maths terms, that's equal to P divided by Q, okay? That's the slope of that line, is the height, P divided by the horizontal distance Q, right? The distance between the points, okay? Now, what's P? Oh, I wrote that the wrong way around, didn't I? Yeah, no, I didn't. So let's look at P. What's P equal to? P is equal to this height, y2 minus y1, isn't it? In other words, that distance. So let's write that down. y2 minus y1. Again, because remember, y2, y1, they're numbers, they're known values, okay? So that's important. So it's y2 minus y1. And similarly, Q is this distance between x2. So in other words, it would be this distance minus this distance. Okay, so that's x2 minus x1. Now we have our definition of a slope, right? So your slope between any 2 points, right, in the Cartesian coordinates geometry system is m is equal to y2 minus y1 all over x2 minus x1. Box that. That's the definition, okay? That's the first definition. Now, I just want to show you something else. And if that's not clear, come in with the Q&A, but I think it is. I think it's pretty straightforward. Now, let's just look at something else here. And this is important because it came up last year. And if you didn't know this, it would have made things quite difficult, right? In last year's paper. So let's draw a circle. Hopefully I can draw a circle. So I'm just going to take what we did there. I'm just going to transfer it onto a unit circle. So I draw a circle. Okay, not too bad. And I'm going to put that unit circle onto our, that didn't work. Let's try that again. Ah, okay. Try it again. Right, a little bit better. The circle isn't exactly on the center of the square, but you'll get it anyway. Okay, center of the cross, I should say. So again, let's do the same thing here, right? And we'll just look at this point here, any point at all on the circle, okay? Now, it's a unit circle, so that means that the distance, the radius is 1. Okay, so let's draw that there like that. And come down here like this. And let's call this angle theta again. Now, from geometry, right, we know that coordinate that is 1, that's minus 1, and that's minus 1. Because it's a unit circle, you know, the radius is 1. Now, you know from trigonometry, right, if that's 1, so that's 1, that's 1, then that height there, right, is sine theta. So this height here is the sine of theta. To do with the tangent, you know, if you say like the tangent of theta is the sine of the cosine. Well, I'm not going to go into trigonometry too much, but this distance then right here is the cosine of theta. Okay, so going back to this diagram and our definition of is this y2 minus y1. So we could say that the coordinates of this here, right, are cosine. So we call this point, what do we call it? We call it point P, right? Point P, the coordinates of that are actually cosine of theta, sine of theta on the unit circle, okay? So again, let's use this formula down here. We say that the slope m is equal to y2. Now, and then this is 0, 0 here. So we want the slope of this line that makes with the x-axis. I write down x-axis. I write down y-axis. So again, we write down y2. Y2 here in this case is sine theta minus y1, which is 0, all over cosine theta minus 0. So it's equal to sine theta all over cosine theta. No, we know that sine theta divided by cosine theta is equal to tan theta from trigonometry, okay? So we have our second definition. M equals tan theta. Put that in the box. Or you can just do it inversely. You can say theta is equal to the inverse tan of m, right? That's not as important to know. So the first one is. Okay. That's the slope of a line, right? Now we're going to show you some properties of the slope of the line. A lot of you who've done this already before know that if you multiply two slopes and equal -1, then they're perpendicular lines, right? Or if they're the m1 equals m2, then they're parallel. So let's just do an example of that. I'll just leave it there a second so you can all take it down. But yeah, last year's exam question was totally based on this and knowing that m equals to tan of theta. If you knew that, this question was quite easy. Okay, I'll move on. Right, so I'll just draw a graph again. X-axis, the y-axis. Actually, I'm going to redraw it right here. Okay, so we have X and Y. I'm going to draw two lines. First line I draw here is just line, and then we have a point on that line, P, and we just give it the coordinates A, B. Okay, so again, dropping this down, we know that that's A. We can go across here, I'll do it in a minute. And then we have another line. I'm going to draw it perpendicular to it, right? So the perpendicular line here would be somewhere like, again, this could be difficult to draw, like that. That's not really perpendicular, I do put better. Okay, that's pretty much perpendicular. And we come across, so this is A, we go up here, A as well, right? This height A here. Let's go across there. At that point. We call it Q. Right. So in other words, I'm saying is that angle there is theta, right? So obviously that they're perpendicular, this is 90 degrees. Okay. Now, so if that's A, right? So in other words, what I did here is I just swung the line. I just cut the line and I swung it, right? So obviously the length of this length here, the length of this line, we call it L, right? So in other words, the length of this line is the same length as this line, okay? So what I'm actually do to make it simpler is I go about that. Yeah, we'll go about that. Okay, hope that's clear. We better go back to the pen. Now, looking at the red line, first of all, right, we can say that the slope of that line, so if that's A, and we'll say that's B, so we'll just go across here. It's B there, right? And similarly, because it's the same, right? If we come down here to black, that's minus B there, okay? That's so in other words, the coordinates of this are minus B, A. Right, now we've set up. Now we want to see what happens if we get the slope of this one and the slope of the black line, right? So the slope of the red one is M, let's call it P, is equal to B minus 0 all over A minus 0 is equal to BA. Okay, now MQ, similarly, is equal to, look at it now, right? So it's Y2, so in this case, Y2 is A, right? Isn't it? Yeah. It's minus A. So we do it the other way. It's 0 minus A, because this is, sorry, this is 0, 0. I should have said that. So the first one, this one here is for this line, and this one will be for this line, okay? So 0 minus A all over 0 minus B. Y2 minus Y1 all over X2 minus X1, right? So X2 in this case is 0, and X1 is minus B. So that ends up being minus A over B. Now, if we multiply MP multiplied by MQ, we get something funny. We get B over A multiplied by minus A over B, and that's equal to, they cancel out, minus 1. So that's why we're saying by definition. So I write the definition, I'll get rid of this. So the definitions then at the end, right, are if you have two slopes of two lines and you want to see if they're perpendicular, multiply them together. So in other words, this is the sign for perpendicular. The perpendicular, M1 multiplied by M2 is equal to minus 1. And similarly, you can work it out as well if they're parallel, but it kind of makes sense anyway. So parallel lines, M1 equals M2. Okay, that concludes slope of the line. So let's go back on it there again quickly. So we had our definition, which is m is equal to y2 minus y1 over x2 minus x1. And when we transfer that then to the unit circle up here, we found that m is equal to the tan of theta. That's the definition. So put that in the box. And then maybe the last box is just this. We just looked in this case, we just looked at two lines that were perpendicular to each other and just to see the properties of the slopes when you multiply them together. So that's just the definition. If you multiply the slope of the red line, multiply by the slope of the black line, you get -1. Okay, so in other words, if lines are perpendicular and you multiply their slopes together, you get -1. Okay. So the next one then is equation of the line. Okay. So if we take the slope formula that we had in the section 1, slope formula, which was, as we defined, m is equal to y2 minus y1 x2 minus x1. Now, in this case, they're known values, y2, y1, x2, x1, they're known, right? Now, in this case, we're going to say, I'll write it down here, let's let x2 and y2 be unknown. In other words, we make y2 and x2 y and x, right? And in this case, then rewriting that formula becomes m is equal to, so y2 becomes y. So it's y minus y1 all over, and x2 becomes x, so minus x1. The reason we're doing this is just to write a more general form equation of the line, right? Just to show you different versions. When you know the two lines, 2 points, you use the one at the top, this one. If one of the points is unknown, you use the second one, right? So rewriting that, then we get y minus y1 is equal to m into x minus x1. Let's box that. I think this is called the slope form of the equation, right? Doesn't matter about all that. Now, you use that a lot. If you're given the point and the slope of the line, you can write the equation of the line using this formula, okay? Now, let's just break that down a small bit. I'll rewrite that. Let's get the y's to one side. So if you just say y is equal to, and then that the y1 becomes across the other side, and I'm going to open this out so it becomes mx minus m times x1 plus y1. Okay, that's all okay, isn't it? Did I write that correctly? I did. So that becomes y is equal to mx. And I'll just write this a different way, right? Plus y1 minus mx. Now, looking at what's inside the brackets here, right? So inside here, y1 is a known number, m is a known number because it's a slope, and that should be x1 there. x1 is a known number. So they're all numbers. So if you subtract a number from a number, well, it's a number, right? So in the more general case here, we write this down as y is equal to mx plus c. C is a number, okay? So again, that's just another form. They're the exact same equations, it's just I wrote them out. And instead of having y minus mx1 all the time, which is a number, I just changed it to c. So again, this is known as the slope intercept form equation, right? Again, you don't need to know that, but that's what it is. So now we've written the equation line in 2 different formats, and you can use them. Like, for example, let's just look at this one just to break it and make it more real, right? That could be like something like y is equal to 4x plus 10. And you're all used to seeing something like that, right? And again, this one, this could be just written as, y minus 10, because again, when you got the subscript, it's a number, equals 4 into x minus 4, right? Something like that. Okay, so no, they're not the same. I just wrote down random equations there. So there's just 2 ways of writing writing the equation of the line. Now, I'll just show you this y equals mx plus c graphically, okay? What I'll actually do is I'll do it up here on the same page. So I'll get rid of all that. So if I just do a graph here. And I draw a line like this. Okay, so this is the line y equals mx plus c. Now, what I'm going to do here is really important, actually, right? So pay attention to this, right? If you get any line inside in an exam, like y could be y equals 4x plus 10, right? And you want to find where it cuts the x-axis and where it cuts the y-axis. I know a lot of you know this already, right? But it's really important. All you do is this, right? For this point, right, what do you notice? So for this point here, I should say, sorry, you can't see me. So this point here, right, x is equal to 0, isn't it? Because if that's the point 0, 0 there. So at x equals 0, so we let x, sorry, that's be funny. X equals 0. What's y equal to? Y is equal to, and x is equal to 0, y is equal to c. So we know the coordinates of this here are 0, c. Okay? Now, similarly, we can find this point here. So all along that line, y is equal to 0. So y is equal to 0. X is equal to, filling in there y equals 0 into this formula, you get that x is equal to minus c over m. So in other words, the coordinates of this one here are minus c over m 0. Okay? What I did there is important, right? Because in a lot of these questions inside of the exam, they don't give you the graph. But I tell you, when we come on to last year's paper, if you just took 30 seconds to draw the points onto a piece of graph paper, you knew what they were looking for straight away, and the answer became clear. So always, you know, put your points onto a graph paper just to see what you're looking at, you know, because sometimes it's hard to visualize it. So I would always recommend doing that. And this is a good way of drawing a line, actually. So if you have any random equation like this, just find out where it cuts the y-axis and the x-axis, and then you can draw two lines through those 2 points, and that's your line. Okay, so it's a very easy way to draw a line given an equation. Now, there's a more general form of the equation as well, so I'll do that on the next page. So this is called the general equation of a line. This is still part 2, right? So the general equation of a line, as you all know, is ax plus by plus c equals 0. Okay, again, the same thing, it's the same way as y equals mx plus c, it's just writing it in a different format. Okay, now that's the general equation. I'm going to put that into the y equals mx plus c, right? So I'll just put y equals mx plus c here, right? That was the other way. I'm going to change the general equation into this format. So let's just write it down as by, keep by, the y's terms on the left, and put everything else on the right, because that's what this is doing here, right? So it's y is equal to minus ax minus c, isn't it? Yeah. No, let's divide across by, so we want this in this format, so we divide across by b, so y is equal to minus a over b x minus c over b, right? Now, that's taking the general equation line and just changing it into the slope equation, okay? Now, let's look at this, right? That m there, that's the slope, isn't it? What do we have here? Minus a over b. So in this case, you can say that the slope of a line is equal to minus a over b. What does that mean? Right, if you had an equation like 7x plus 4y plus 10 equals 0, right? Say in an exam or wherever you are, can you get the slope of that line? Whew, be difficult, wouldn't it? But if I tell you that the a here, right, is 7, and the b is 4, then you know straight away using this formula that the slope of that line is equal to minus 7 over 4. Okay? I just want to check that that's right. Yeah, it is. Okay, so if you get an equation in this format, which is ax plus by plus c, right, equals 0, you can tell me the slope of that straight away just by using this formula, just by taking the A and the B, okay? Simple. In other words, it doesn't matter what the C value is. The C value could be anything, it could be 7,000. The slope is only dependent on the X value and the Y value, okay? Now, if I had more time, I'd show you that graphically, but it's quarter, we move on. Okay, so that's pretty much everything on the slope and the equation of the line. The third part, now the next 2 or 3 are actually quite quick. So they're like more like definitions. So the next one is going to be the area of a triangle. By the way, if you understand the first 2, the rest are just like learning off formula. And I think some of them formula in your logbooks anyway. So the first 2 that I just did there are the most important I'm going to do today. Okay, so X and Y. Say you're given a triangle, like that. Okay, that's a triangle, and you're given the vertices. Let's say they're let's see. Might do an example. I'll do an example in a minute. Let's say that's A, B, and C, right? And that the formula for a triangle, I can write it down. So the area of a triangle is equal to a half times this x1, y2 minus x2, y1. The problem with this, right, is only gives it 2 vertices, isn't it? X1, y1, and x2, y2. But we have 3 points. So the trick with this, right? I'll write down the definition. With vertices 0, 0, x1, x1, y1, and x2, y2. That's the definition, right, of the area of a triangle. The problem is generally like one of our vertices isn't 0, 0. So what we must do is something called translation, okay? So in other words, we have to translate this triangle and make one of the vertices 0, 0. So in this case, look, I'll move CC to 0, 0. So that becomes 0, 0. But I must do the same to the other ones. In other words, what I do is I'm going to catch that triangle and move it down. So like just catch it and move it down, right? So I'm going to move down. So C goes there. So that's our new C. We call it C prime, right? Doesn't matter. And B is about here if I do the same thing with that. So if I move the same distance, about there, I'd say, right? This won't be exact. Don't worry about it. We call that B prime. And similarly, we move A the same distance. So A will go somewhere about there. That's A prime. And I'll redraw the triangle. So that triangle is the same area. Might not look it right because I didn't draw that absolutely perfectly. But now at least one of the vertices is on 0, 0. So that B1 that could be x2, y2, and that can be x1, y1. Now, the best way to do that is by an example. So I'll just do an example here. So I'll maybe do it down here, might be easier. Okay, so the question is, find the area of a triangle with vertices. A is equal to 3 minus 1. B is equal to 4, 2. And C is equal to minus 1, 3. That's the way they come in an exam as well, right? Usually. Now, the problem here is that none of our vertices are 0, 0, right? So we have to catch one of them and make it 0, 0, okay? So in this case, we make this one 0, 0, okay? So we just catch A, right? And we make that 0, 0. Now, this is the trick in this whole thing, right? To make that 0, 0, right? What we did is we did 3 went to 0, so that was minus 3. In other words, we subtracted 3 from the x coordinate. And to make the y coordinate 0, we must plus 1. Okay, so 3 minus 3 is 0, minus 1 plus 1 is 0. Now, what we do to 1, we must do the exact same to all the others, right? So 4, 2 similarly becomes 1, 3. With my 4 minus 3 is 1, 2 plus 1 is 3. And similarly, the last one becomes minus 4, 4. So now we have 3 new vertices. All we've done is catch the triangle and move it, still the same area. So that's what we're asked, right? So then the area of a triangle, by definition, we know the triangle, area of the triangle is half x1, y2, which is 1 times 4 minus 4 times 3. So that's equal to a half times 4. Sorry, make the vertical. 4 plus 12. So it's equal to half times 16 equals 8. Okay, so the area of that triangle is 8 square units. 6 square units. Okay, that's the area of a triangle. Quick, not much to it, okay? And I think that is in your logbooks. Okay, let's go on to 4. 4 is the perpendicular distance. I have the perpendicular distance. I'll write it out. Okay. So what does that mean? It's just a formula. Again, did it come up last year? It came up in last year's paper, this one, right? So again, you have an x and you have a y-axis. And in this case, I just draw a red line. Any red line, doesn't matter. And you have some random point P here, right? So this is your point P with the coordinates x1, y1, okay? Now, the perpendicular distance from P to the line L is what we're looking for. So this is the line, I'll write this down in line as well. So this is the line L, right? And we give it the general equation. You can do whatever you want, but in this case, it's the general. So it's AX plus BY plus C equals 0. So what we're asked is to find the distance between P. Let's do it. The perpendicular distance. So let's draw a line to know that's perpendicular. And we call this distance, right? We call it W. Call it whatever you want, really. So W, that's what we're looking for, okay? Now, the formula states the following. W is equal to A times x1 plus B times y1 plus C all over square root of A squared plus B squared. Put a box around that. That's your formula. So in other words, all it's saying really is, look, the A is the A from this equation. So for example, there is a proof, right? But I'm not going to do the proof because we don't have time for that. So I might do a quick example on this, right? So the question is, find the perpendicular distance between the point 4 minus 1 and the line 3x minus 4y equals 7. So that's a little bit tricky the way I wrote down equals 7 there. So let's put them both. So first of all, I'm going to look at the equation, right? So in this case, our line L, we call it L, right? I'm just going to rewrite L into the form, the general form. So it's 3x minus 4y plus C, that 7 comes up minus 7 equals 0, right? And our point in this case is P, right? Or x1, y1, P, which is x1, y1 equals 4 minus 1. So then we can just plug that in, right? That's important, to just write the equation in the same format as the general equation. So then we can write down that our distance W is equal to, still exactly like that. So it's 3 times 4 minus 4 times, and y1 is -1, -7, all over the square root of 3 squared plus 4 squared. I think it's important just to do examples, quick examples, just because when you look at letters and numbers, it can get a bit tiring. So in this case, that works out as 12 plus 4 minus 7 all over square root of 25. So that's 12 plus 4 minus 7 is equal to 9, and square root of 5 because 25 is that, so it's 9 over 5. I think that's right. Okay, that's another one done. We've only 2 more to do, and then we're finished the background, right? And then we do some papers. But I think it's important to understand what I'm doing now, because doing the papers then is easier afterwards. So 5 is this is probably the trickiest one actually, angle between 2 lines. Formula. Okay, so I just draw a graph again. And let's pick 2 lines. We'll be using a lot of slopes here now, so remember that from chapter 1. So that's, we call that we call it L2. And this has a slope of M2. Okay, and we draw another line. And we call it L1. We'll just do it like that maybe. So let's call this line 1. And this has a slope of M1, right? Now, the angle that it makes, remember the slope is like the angle that it makes with the x-axis, right? So in this case, we call it alpha, right? And for the line L2, we call the angle that it makes with the x-axis beta. So we have alpha and beta, okay? Now, what we're looking for here is the acute angle between the lines, okay? So that's, I'll give it a different color. This is theta. So again, angle between 2 lines. What we're looking for, there's a formula for the angle between those 2 lines, right? Now, if that's theta, then this angle here, right, is 180 minus theta. Okay? Because that's a straight line. If you cut that, if that's theta, then the other one is 180 minus theta. Okay. So going back to the slope formulas, right, we say that M1 is equal to tan of alpha. Remember I did that way back in page 1 this morning, an hour ago. M1 is equal to tan of alpha, and then slope 2, M2 is equal to tan of beta. That's just definitions, right? Now, you probably remember this from junior cert. Do you remember, I can't remember the wording, but the sum of the 2 internal angles equals the external angle, right? Do you remember that? So in other words, that in this case, alpha is equal to theta plus beta, right? Just rewriting that, you can say that theta is equal to alpha minus beta, okay? Therefore, just taking this, you can write down then that the tan of theta equals the tan of alpha minus beta, okay? That's just a bit of trigonometry, which I hate, but that's just all definitions, right? So in other words, what we're looking for is the angle. So we're looking for this theta, right? So we've just taken 2 definitions. We know the slope of this line and we know the slope of the other line. And all we did, we just took that. This is probably the most important bit, that you can identify that alpha is equal to theta plus beta. But then you just reword it. We're looking for theta, so we can say that theta is equal to alpha minus beta. But that's not in the formula that we want. So we're just looking at this, tan of theta is equal to tan of alpha minus beta, right? Now, from the log books, and this is in the log books, there's an equation for that, right? So tan of alpha minus beta can be written in another way, and that's this. So tan of theta then is equal to the tan of alpha minus the tan of beta all over 1 plus tan of alpha, tan of beta. And this is the most horrible thing I'm going to do this morning, by the way. So again, we go back up to the definitions here, look. And we're going to write it in a much nicer way. So then we can say that the tan of theta is equal to m1 minus m2 all over 1 plus m1 m2. Okay, so therefore, writing it another way, I'm not going to get into too much geometry here, but I'm going to write down the final answer here, right? So theta then, right? So this is what we're looking for along with the angle between two lines. That's defined as then the tan inverse, basically just bringing the tan across, tan inverse of m1 minus m2 all over 1 plus m1 m2. That's the definition, right? The reason we have the, well, I forget what they're called, but it's, you know, everything inside the bracket is called, they're positive, right? Is because there's two angles. There's the 180 minus theta as well. But look, I think the important thing to know here is this. And don't get too worried about all the background. I just wanted to show you where it came from, okay? Now, I'll go on to the next page, right? Just remember that if L1 is parallel to L2, if the two lines are parallel, then the theta is 0, okay? That's an important thing to know. And if L1 is perpendicular to L2, then theta is equal to 90 degrees, right? So, you know, it might be better to do examples with that later instead of getting, but actually, what I'll do just for your notes, I'll write it out, okay? So if L1 is parallel to L2, that means that the angle between them is 0. That makes sense, doesn't it? Like there's no angle between those lines. Theta is equal to 0 degrees. So in other words, we're saying then that the tan inverse of m1 minus m2 all over 1 plus m1 m2 is equal to 0, isn't it? So then, in other words, that's equal to 0. So that we're saying then that m1 minus m2 is equal to 0. Therefore, m1 equals m2. Okay, that makes sense, doesn't it? They're parallel. So in the second case, then you'd have L1 is perpendicular to L2. Therefore, the angle is equal to 90 degrees, isn't it? Two lines are perpendicular, you know, that's 90 degrees. So in other words, the tan of 90 degrees is indeterminate, isn't it? So that basically says then that's what's below the line, 1 plus m1, m2 is equal to 0. Because if you just divide a number by 0, it's undefined. So then in other words, for this one, it was what above the line is equal to 0. Here it's below the line is equal to 0, right? So in this case, you'd have m1, m2 is equal to -1, which is what we learned earlier. Remember, if we multiply the two slopes that are perpendicular, you get -1. Okay, that's just an aside there, but just bear it in mind and write it down and look over it. It'll make sense when we start doing examples. Okay, 2 more to go. So number 6 is the divisors formula. Divisors. Okay. So we have a y-axis. 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 X-axis. We have a line. Any line. Okay. And on that line, we have 2 points. The start of the line is A, and the end of the line is B. Now, what we want to do is divide that line up somewhere, right? So we'll just say here, that's the point C. Now, again, A and B are known, so we give them the standard notation. So it's x1, y1, and x2, y2. Now, what we're trying to find here is the coordinates of C, okay? Now, the line is divided up into the following ratio, okay? This is the ratio R. This is the ratio S. Again, I'll do an example in this later and I'll make it see. In other words, that could be R could be 2 and S could be 1. So that C divides that line up into ratio 2 is to 1, or R could be 5 and S could be 3, right? So 5 is to 3. Now, this is the internal divisor. We don't do external in the leaving cert anymore. So the coordinates of C, internal divisor, right? So C is equal to internal divisor, and the coordinates of C are given the following. I'll write it down here and make more space. Is equal to S times x1, x1 plus R times x2. Now again, because it's x1 and x2, they're numbers, they're known values. All over S plus R and S times y1 plus R times y2 all over S plus R. Okay, that's the definition. So I just write down here C, put it in the box. Okay, that's what you need to know, okay? Now, what happens if S is equal to R? Oh, I just do one thing before I do S. I know I do it now. So if S is equal to R, that is if they're divided up. So in other words, R is equal to S, right? So in the ratio 1 is to 1, or 2 is to 2. In other words, C is the midpoint. So if S is if S equals R, therefore C is equal to the midpoint. So if S is equal to R, we see what happens. Let's fill it in. S is, in other words, instead of writing R out, I write out S out. So then C is equal to S x1 plus S x2 x2 all over S plus S. And then you have S y1 plus S x, or sorry, do that again. Y2 all over S plus S. Now all the S's cancel out and you're left with C is equal to x1 plus x2 all over 2, y1 plus y2 all over 2. So that's, we call that C midpoint. Now, I went through that quite quickly because it's quite straightforward. But it's very easy to make a mistake. And just notice one thing here. I'm going to do it in a different color. Note the S is with the x1. So the S is this one here, is with these values here. So the S goes to x1 and S goes to, so that was this, look, sy1. See, the S goes to the opposite one, right? I could do it just a quick way of reminding it, right? So that, in other words, inside an exam, remember that the ratio that's furthest away goes to the furthest away point, okay? Maybe I'll give you an example. This is a beam, right? See, this is a beam, right? And it's just, you know, two supports on the end of the beam. We call that F of A. We call this FB, right? In other words, that if you put a load on that, say 20 kilonewtons, right? Or 20 tons, we'll say 20 kilonewtons. And this is a 10-meter long beam. So this beam, I'll write it in gray. So it's 10 meters long. And say that point low there, right, which could be a person, is 8 meters from here. So obviously it's 2 meters from here, right? Now, looking at that, right, if there was two people holding up a board, right, and there was someone standing on the board, who's going to feel like they're carrying more? Intuitively, you look at it and say, well, the person B is carrying more, isn't he? Definitely. And he is, because the person at A is actually carrying, A is carrying 2 times 20, which is 2 over 10 multiplied by 20. So he's actually carrying 4 kilonewtons, and the person under B is carrying 8 over 10 multiplied by 20 equals 16 kilonewtons. Look, that's just a way of reminding that's actually an engineering formula, right? It's just for carrying or checking out forces. In other words, that the person closer to the 20, the load, so FB, this person is multiplying by 8, which is the distance that's further away. Look, it may help you. It certainly helps me anyway. Okay, the last one we're going to do is the distance formula. Okay. Y-axis, x-axis, and let's just pick 2 points. So we draw a line first. That's the line A, B, So B is x2, y2, and A, x1, y1. So it's a distance form. We want to know the length of that line, okay? So very important again to do that. Let's go down this way with dotted lines. Here with dotted lines. Let's go horizontally. Okay, so we know that that's x1, that's x2, that's y1, that's y2. Okay, now just complete the triangle here, okay? And I just change color. And let's call that point C. So if you remember back to Pythagoras, you have a triangle like this. And this was A, this was B, this was C. Then we know that C squared is equal to A squared plus B squared. Pythagoras, isn't it? Very good. Now in our case, our C in this case is AB, and that's what we want, right? So we can write down so that AB is this distance here. Okay, everybody knows. So AB, that's what we want. So we can say AB squared is equal to AC squared, which is this distance. So that's AC. Yeah. Times CB plus CB. Okay, that's right, isn't it? So we can say that AB is equal to the square root of AC squared plus CB squared. Now let's write down what AC is. What is AC? Well, AC is just x2 minus x1, isn't it? Because I'll do that. So in other words, this distance here, that's x2. And this distance to here is x1. So the distance between them, this distance, what we're looking for, is just x2 minus x1. And similarly for the y coordinate, right? So let's fill it in. So AB is equal to the square root of x2 minus x1 to be squared plus y2 minus y1 to be squared. And that completes everything on the course, right? There's only 7 things to know. We already spoke about we'll do an example with collinear lines, and I'll give you some more tips and tricks, right, after the break. So now it's 11:10 now. I think we'll take a break now, Eamon, maybe come back in 10-15 minutes, maybe let's say 15. So we'll come back at 11:25. Okay, guys, you can see my screen, you can. Okay, so just before we go on to the exam papers, right, I just want to give you a few extras, right, just things that could help you in an exam. The first thing there, right, and it did come up last year, is so I just got it, look, collinear points, right? And as I say, the best thing now we'll do last year's paper. So like, you know, if you have a line like that and you have the point P, and P, Q, and R. Okay, you might be asked in an exam, prove that they're collinear, in other words, that they're all on the same line. There's a few ways you could do it, right? You could find out that, you know, PQ, the length PQ, right, plus QR equals PR. Kind of, that might, yeah, that would prove that it's collinear, wouldn't it? Yeah, it would. Second one, right? Let's say, is the slope of PQ, is it equal to the slope of QR? Well, you know, because you're using the point Q for both of them, so yeah, that's another way. But I think the best way, right, is to prove that the area of the triangle PQR equals 0. Now, I gave this tip to people last year, obviously, on this course, right? And well, it came up in question 1 last year, okay? Question 2, actually. Question 1, part B, that exact thing came up. So we'll do that next, right? And then some more little tips. Points on the same, if you're given 2 points, right? So if you're given, say, x1, y1, and you're given x2, y2, okay? If you're given 2 points like that, right? And you're given, let's say the line, we'll just call it ax plus by plus c equals 0. And you might be asked, like, you know, are they on the same side of the line? So in other words, like, you know, say if that's the line L here, right? For example, let's go back to the other diagram. That's the line L. And say you the point A here and the point B, and you're given those coordinates that you're asked, are they on the same side of the line or are they on opposite sides of the line, okay? What you do simply is you plug in the x1 into this equation. So change x with x1 and change y with y1. So just do it like that, right? And just exchange them in, right? And this is the solution. If you get a positive answer by filling them in, let's say for if this is, so there's three cases. It's the same sign, positive or negative. Therefore, they're on the same side, right? So if you put in x1 into that equation, you come up with -5, and you plug in the other one, x2 and y2 into that equation, you get -10. Then they're both negative. That means it's on the same side of the line, or the opposite. If they were both positive, then you say they're on the same side of the line. And obviously, part 2 of that, if you have different signs, therefore they're on the opposite side, right? That's kind of obvious. And the final one, 3, is if it equals 0. If it equals 0, in other words, if you put x1 and y1 into that equation equals 0, then it's on the line. Okay, that's just the tips. So we've actually completed the whole course there, right? That's that done. Now we've got to some papers, right? Some past papers. Just one other thing, right? Just to prove to you that maths is used in the real world, right? I'm going to change my screen here now to stop sharing that. I'm going to share this one. As I said to you last Thursday, this happened to me, okay? I got a text, an email. I'll show you the email, just so you know I'm not making it up. I don't know if you can see that, but it says, I'll read it out to you. It says, Mark, the 2 coordinates I have on the wall already poured are as follows. X, and the X coordinate is 6747370.308, Y, blah, 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 and the other coordinate. I have 2 coordinates, right? So the guy on site, now I'll show you the job. I'll go to PR1, 2, that's the bridge, okay. So this is a bridge up in Carlow, okay? It's piped forward. In other words, it's like it's a series of 11 pipes there, okay? And they poured a load of concrete over it and people drive over it. This bridge floods regularly, okay? Upstream and downstream. You'll probably see why in a minute. Like that's it, it's a mess, right? You can see not much water gets through that bridge, and it's a big river. It's called the Mountain River, right? Maybe that's a better photograph, right? So you can see it's not a great bridge, right? So we took it out. And we're currently building this bridge, okay? And maybe I have the latest photograph. So this wall is poured, okay? This is one of the abutments poured. Now, the guy gave me the coordinate of this point and the coordinate of this point, right? He had a GPS in sight. He planked it down. He gave me those 2 coordinates. Now, bear that in mind, okay? This is what the site looks like at the moment. That's the old bridge there being taken out, right? And we poured the other wall here. And we have to pour another wall here, okay? And on top of that wall would become, if you remember earlier, we had the precast beams. I got any photographs? So this is the wall poured from behind there. This is the wall it's in. The one on the far side isn't being poured. They want to set it out. So I got that email. These are the coordinates. What are the coordinates of the other side? So I'll show you what happened, okay? So again, this is a model of the bridge, okay? So let's say this is the long stream. So this is the existing bridge, okay? That's what we have. We're going to take that out. See this height here at the top of the rail? That's going to be the bottom of our new bridge. So in other words, that's height. So what we're going to do, we're taking out the whole existing bridge, putting in a much bigger structure so that it can take the flow, okay? So that's what it looks like a plan. Now, the walls that you just saw cast are this kind of inverted T, right? This one is being poured, okay? Now, they want to set out this one. And obviously you can imagine it's very critical to get the setting out of this correctly. If this wall is, maybe I can do it now. If this wall is, for example, if we set it out too far back, the beams don't build the bear on it, right? And if it's too close, then we don't get enough capacity, okay? So that needs to be exact. And we have a tolerance of about 10, 20 mil. We have to get it right. These are the beams, what I'm highlighting, they're the beams that are coming in. They're being made up in Banagher in County Offaly, which we're all too young to know pure mule, but that's where that was set. So there's a big factory up in Banagher that make these bridge beams. So on cross sections actually look like this. So that's these beams. That's looking through the deck. So that's the shape of the beams. And there's 5 of them, and they're coming on site. And as I say, they need to sit down on top of these walls. Now, I got those 2 coordinates. So what I did then, so on plan, I'll show you this. Okay, plan, my deck plan. That's the plan of the bridge, okay? I'll show you a better plan. So again, that's the river there, right? These are the walls, they're kind of in at a skew. So the dotted line here that I'm going around, that's the wall it's in. This is actually the wall here, and that's the base of the wall. So this is the wall here, and those beams are going to be landing on top of the wall, okay? So right, I caught this then, right? So now see this, what I'm going to highlight, that's the wall. So he gave me the coordinate of this point, and he gave me the coordinate of this point, right? So what I did then is I cut this drawing, put it into a separate drawing, and I created this drawing. Now, I'm going to zoom way out here because that's 0, 0. You know, on our, I can zoom right in here with zoom. See, that's your y-axis, that's your x-axis, and that's the origin 0, 0. He gave me those two coordinates. So I put in the x coordinate here. If I zoom in right in here, now you'll see the third one. Don't mind the third, that's the midpoint. I'll talk about that in a minute. So he gave me this coordinate and this coordinate. And I put in the x coordinates and I put in the y coordinates. I have to zoom way out, and this is the point here, right? Now, I'm just going to turn that off. So he gave me this coordinate and that coordinate. That's the corners of the wall. And then I just got the wall and I clamped it on. Right? So that's the wall, the drawing there, right? And I clamped on the wall at that coordinate and that coordinate. And then based on that, then what I did is I just cut, this is called SketchUp, is a program I use. I just gave him the coordinates. See the coordinates there popping up, 6, 7, 4, 3, 7, 4, 8, 9, 1.7. I gave him those coordinates, sent them back to him. He checked on site to make sure he's in the right place. And this actually happened. Now, to make it further complicated, on site, they made this wall longer than I had on the drawings, which isn't the problem. It would be a problem if it was shorter. So what I did actually is I got the point here. So you can see it there, 6, 7, 4. I don't know if it's maybe too small for you to see, but I can see it. And I got this point here. And I promise you, I did a separate spreadsheet. I used the midpoint, you know, the divisor's formula for the midpoint. And I got the midpoint here, okay? And once I had the midpoint, I gave him that to make sure that's what was on site. And I actually gave him then the corresponding midpoint on the other side. And I did use a spreadsheet, and I did use all the formulas that we used it this morning. So look, that's just showing you quickly that, you know, it can be used in the real world, and coordinate geometry is easily used in the real. Okay, I'm going to change back to one. Okay, so let's do some examples. And as I said, I did the 2020 this morning myself, so I haven't checked if the answers are correct. I think they are right and they look right. So let's move on. Okay. Just add more pages. Right. So this is 2020 paper 2. Okay, maybe I'll draw it in red. So you were given 3 points, and the points are as follows. This is part A, question 1. And A. We were given 3 points, A, which was 2 minus 6, B, which was 6 minus 12, and C, which was minus 4, 3. Now I'll read out the question. It says the coordinates of 3 points are A, 2 minus 6, B, 6 minus 12, and C, minus 4, 3. Find the perpendicular distance between A to BC. Okay, so let's go back. Remember our, so again, what I did this morning with this now as well, and it straight away I knew exactly what we're going to do. I actually drew out the points on the graph, right? So it's something like that, right? Now, it doesn't need to be exact, but it kind of gave me an idea. So that's why that's X. So 2 minus 6 was roughly over 2 minus 6, roughly there, right? So that's A. And I'll just give that. So that's A. And then B was about 6 minus 12, so about here, roughly. Doesn't have to be exactly the same. So that's the point B. And then point C was minus 4, 3. So minus 4, 3. That's minus 4, 3 about here, right? Okay. So I just drew a line into that. I won't do it yet. I'll just look at the points. So I'll do the answer over here. Okay, so remember the perpendicular distance between the line and the point formula was W was equal to AX plus BY1 plus C all over the square root of A squared plus B squared. Now looking at what we have, right? Do we have the point? Yes, we do, because it says between A, so A is the point, right? So let's write that down here over here. Look, A is the point, 2 minus 6. So that's our x1 and y1, isn't it? x1, y1? Yeah, so that's x1, y1. So we have our x1 and y1, but we don't have our ABCs yet. We don't have that general equation of the line, right? So like we have this point A, and we're finding the distance from A to the line CB. So let's draw the line CB. That's what it's asking, our BC. So let's draw BC. That's the line BC there, okay? That's the perpendicular between A and BC. But we don't have the equation for the line BC. So remember at the start there when I was saying you find the slope, you know the equation of the line. So do we know the slope of the line BC? So look, we're looking for the equation of BC, right? We don't know what that is. But do we know anything about it? We can find out what the slope is because we have the coordinates, can we? So let's start with that. So let's say M, the slope of the line BC is defined as y2 minus y1 over x2 minus x1. Just to be clear here, what we're trying to do here, we're trying to find the equation of the line BC. So that's why I wrote down EQBC there, right? But we don't know anything yet, but we do know slope. We can find out the slope is y2 minus y1. So in this case, it's 3 minus 12 all over minus 4 minus 6. I'm working all that out, you get minus 50, right? Minus 15 over 10 is equal to minus 3 over 2. So now we have the slope and we have a point on the line. And do you remember the more general form of the equation? Remember we wrote down y minus y1. So I won't do that. Y minus y1 is equal to m into x minus x1. Remember that? You just fill in those values. So we just pick y minus y1, which is minus 12. So it's plus 12 equals the slope, which is minus 3 over 2 times x minus 6, right? That's from y minus y1. Okay. So working all that out, we get that I'm cutting corners a small bit here because it's not important. We end up with 3x plus 2y plus 6. What's important when you're doing this, right, is your minuses and your pluses and bringing the minuses across the other side. You can make a lot of mistakes. I do anyway. So now we have our equation now, don't we? So we have our equation, we have our points. So that's our equation. I just put it in the box, but that's our equation. And that's our point. So that's the equation for BC. Let's write down BC there. So now we can fill that into the formula above, so that becomes W is equal to A in this case is 3, x1 is 2. So you're going to take 3 plus 2, right? Plus 2 times minus 6. I put that in brackets, it's clear. But plus 6. Okay, all over square root of 3 squared plus 2 squared. Working all that out, you get 6 minus 12 plus 6, and that's equal to 0. 0 over root, whatever it is, what is 9 plus root 13, isn't it? So that's equal to 0. So what's that telling us? So at the very end here, it says, it says here, look, distance, and it says conclusion. Well, our distance we can write down, so your answer here, right? Distance equals 0, and your conclusion is, this is in UCC now, I'd ask you on, I'm sure it'll all say co-linear. Remember the last page? We said that the distance, or sorry, yeah, look, it doesn't matter, I didn't do it on that one, but yeah, it's the same. So the conclusion is collinear. What does that mean? The distance between A, the perpendicular distance from A to the line BC is 0. So in other words, it's on the same line, therefore it's collinear. Okay, that was part A to that question. Part B then, I have to draw a diagram for you. Again, not a very difficult question, right? But again, it's all about the angle of the lines and the tan theta. That's so important here, right? So you were given the y-axis, you're given the x-axis. So this was given in the exam, right? This was the line A. I'll try and draw it like they do. Okay, this was called the line A. And then we were given another line here. Okay. This was called the line B. Again, this was given 60 degrees. And this was the line theta. And then A was called x minus 2y plus 1 equals 0. Okay, actually wrote down here x, and they wrote down y. They gave you nothing else. Now, it says, the diagram below shows two lines, A and B. The equation of A is x minus 2y plus 1 equals 0, which we've written down. The acute angle between A and B is theta. That's this theta here. And line B makes an angle of 60 degrees with the positive sense of the x-axis as shown in the diagram. And then it asks you, find the value of theta in degrees, correct to 3 decimal places. So again, but I'm sure you all do the same as well. Let's write down what we have. So we have A is x minus 2y plus 1 equals 0. Now, we also know that the slope of the line B, so we call it m subscript b, is equal to the tan of 60 degrees. Do you remember doing that? The slope of a line is equal to the tan of the angle, right? That it makes with the positive x-axis. In this case, the tan of 60, right? Because it says 3 decimal places, I worked it out straight away. Using your calculator is 1.732. No need to go any further, it's 3 decimal places, right? What else do we have? Remember the angle, the angle was the angle between two lines, the acute angle between two lines, and we were given the slopes of the line. So we need to find the slope of A. We have the slope of B, right? What we don't have is m of A. So we write down what's the slope of A? We don't know. Let's find it out. Remember the last time, like this equation up here is in the form of ax plus by plus c equals 0. Let's put it into the format of y equals mx plus c, and then we can get the slope straight away. So we have x minus 2y plus 1 equals 0. Let's get into the format now, right? Let's get the y's on one side. So you have minus 2y is equal to minus x minus 1. Dividing across by minus 1 or dividing across by 2, you get minus 2. You get y, so divide by minus 2, right? You get y is equal to x over 2 plus a half. Now, in this case, I'll just write it out a different way. It's y is equal to a half x which is in the form y is equal to mx plus c. Therefore, m of A is equal to a half. Now we have the slope of that line, and we have the slope of B. So we have the slope of B, we know is 1.732, so I'll write it out again. M of A is equal to a half, and M of B is equal to 1.732. Now we must go back and remember the angle between the line formula. We go back to this, is tan of theta, the acute angle between two lines. The acute angle between the two lines given the slopes of the other two lines is equal to M of A minus M of B all over 1 plus MA MB. Okay, and in the other formula it was M1 and M2, M1 minus M2 all over 1 plus M1 plus M2. It's the same thing here, right? They're just numbers. So let's fill that in. Remember, theta is what we're looking for. Tan of theta is equal to M of A, which is 0.5 minus 1.732 all over 1 plus 0.5 divided by 1.732. And that all works out as 1.232 all over 1.866 equals 0.66, right? And then that's the tan, right? So therefore, I'll just write the answer here. Tan of theta, so theta is equal to the inverse tan of 0.66. So theta equals 33.434 degrees. That's your answer. Again, it asks the 3 decimal places, so we may as well put it in. I didn't check that, but it looks right. I mean, that's 60 degrees, right? You know, and that looks about roughly half of it. So 23.424, I think is the right answer. Okay, if there's no questions on that, I move on to the next one. So this is 2019 paper 2. Might be able to bring it in here. We'll just have a look, see if I can get this. This might work. Okay, put that over there. Okay, let's try this. Okay, so I presume you can all read that. Yeah, it's big enough. Yeah. Okay, so it asks us here, the line P makes an intercept on the x-axis at A0 and on the y-axis at 0b, where A and B are not equal to 0. Show that the equation of P can be written as x over A plus y over B equals 1. So again, what are we given here? We're given 2 coordinates, 0b and A0, and we're asked to write the equation of the line. Now again, first thing you always do here is think back, when do we get the equation line? From the slope, right? So the first thing I'd always do here is find out the slope of the line. So we say that the slope, let's write down, this is part A. The slope of that line is equal to 0 minus b, y2 minus y1 over x2 minus x1, minus, all over A minus 0. So it's equal to minus b over A. That's the slope of the line, okay? Now, again, generally, we have, you remember y minus y1 equals m into x minus x1, right? So in this case, we just pick y minus y1 in this case is we just pick b, doesn't matter. Y minus b is equal to minus b over a to x minus 0. Now I bring the a across here, so we get ay minus, I mean, ay minus ab is equal to minus b times x. Again, just be a bit careful with the numbers. I'll just give it up there. So that's clear, I think. Look, we got the slope. We found out the slope is minus b over a, and then we put it back into the general form, y minus y1 equals m into x minus x1. So let's work that out. So let's divide across by a. See where we're trying to get this. So divide across by a, you get y. Let me see, am I doing this right? No, let's do something else first. Let's get it into the kind of the ay format. So that becomes ay plus bx equals ab. Just rewriting so it looks a bit more like this, you know. So that's ay plus bx equals ab. So I divide across by a first of all, right? Divide by a, and we get y plus b over ax equals b, and then divide by b, you get y over b plus y, sorry, is that correct? Divide by b, y over b, yes, plus x over a, because the b's will cancel out, equals 1. And then just rearranging, you get x over a plus y over b equals 1. That's what they asked for, isn't it? Now let's look at the second part. Part B says the line L has a slope m and contains the point A 60. Write the equation of line L in terms of m. Right, the line L has a slope m and contains the point A 0, A6 if it's 0, 0. So the slope equals m and the point A60. Let's write out that form again. Y minus y1 equals m into x minus x1. This is a very simple question actually. So like again, put in for y1, that's x1, sorry, that's x1, and that's y1, right? So y minus 0 equals m into x minus 6. So writing that in terms of m, let's say, write the equation of the line L in terms of m. So then we get y is equal to mx minus 6m. Pretty straightforward. Now, the third part of the question, let's write it on the next page. Let's give you a second to take that down. Okay. So it's actually B part 2. I won't put on the what page is there? Should do, yeah. Okay, so B part 2 of that was find the line L that cuts the line K, right? So there you have the line K, and it's 4x plus 3y equals 25. So I'll write down L there again, right? So what they're asking, so the line L was this, right? We just worked it out. L is equal to y is equal to mx minus 6m. Okay, so we have two lines. We have K and we have L. And what it's asking is, find the coordinates of P in terms of M. The line L cuts the line K, right, at the point P, and it wants to know the point P, right? So we have any line K, that's K there, right? We have the line L. They cross each other somewhere, and they wants to know where do they cross, right? So I'm going to just knock these into nicer format. So that's 4x plus 3y. I'm just going to rewrite this one. That becomes minus mx plus y equals minus 6m. I'm just rewriting this one again. It's 4x plus 3y equals 25. So what have we got here? Two simultaneous equations. So let's multiply the top one by minus 3 and this one below by k, right? Sorry, k, yeah, we'll just write it. Actually, if you just multiply the top one, sorry, if you multiply L by minus 3, that would work, won't it? So let's do that. So I'll rewrite them again. It's multiplied by minus 3, you get 3mx minus 3y equals 18m. Okay, so I just multiplied L by minus 3, right? So then you can see that that'll cancel, and you'll be left with 3m plus 4 times x equals, adding 25 to 18, 25 plus 18. M, and then x is equal to 25 plus 18 m all over 4 plus 3m. So what have we got here? We've got the x coordinate, right? We need the y coordinate as well. So to get the y coordinate, we just plug it back into this one, I think is what I used. Yeah. So y is equal to mx, so it's m times x, which is that, which is 25 plus 18m all over 4 plus 3m, and that's minus 6m, isn't it? Yeah, minus 6m. So we multiply all that out, and the best way is probably to bring the 4 plus 3m, so multiply 6m by 4 plus 3m. Again, we'll look, is there just 12 o'clock? We'll do it. So it becomes minus 6m, and so it's m, work on that, so it's m into 25 plus 18m minus 6m into 4 plus 3m all over 4 plus 3m. Then working all that out, you get 25m plus 18m squared minus 24m minus 18m squared. Luckily, the m squared is cancelled, all over 4 plus 3m. Then you're left with 25 minus 24 is 1, so it's m all over 4 plus 3m. So the coordinates of P are as follows: 25 plus 18m all over 4 plus 3m, and m all over 4 plus 3m. Okay, that's what you're asked for, and that's the answer to that one. Okay, so again, not that difficult, really. Like, you know, I mean, it's quite, the only tricky thing was just your simultaneous equations and factoring and all that, right? But not so difficult. Okay, I'll just give you a moment to take that down. The next one we're going to do now is 2018 paper 2 again. Okay. So it's definitely a question, I think, where you could pick up a few points anyway, the geometry of the line. So I don't know if I have this on picture. Let's see. I do. Okay, so that's that one. We'll read it out. It says, the line M 2x plus 3y plus 1 equals 0 is parallel to the line N. Okay, 2x plus 3y minus 51 equals 0. Verify that the point A minus 2, 1 is on M. To verify that line is on a point is on a line, you just plug it in, right? So let's get A. Sorry. So A is minus 2, 1. So you just plug that into the line N, right, which is that. So you fill in for X, so it's 2 minus 2 multiplied by minus 2 plus 3 times 1 plus 1. That equals minus 4 plus 3 plus 1 equals 0. Therefore, true. Okay, A is true. So we verify that. So that's part A. Very simple, very quick. Part B says find the coordinates of B, the point on the line N closest to A as shown, right? So we're trying to find the coordinates of this one, B, right? The point on the line N closest to A as shown below. Right, what do we know? We have A, we know that's minus 2, 1. What else have we got? We can find the equation of M, can't we? Because we know now that we found out from part 1 that A is minus 2, 1, and we have the slope of the line. So we can find out the equation of it, right? So there's a few ways of doing it. We can do the y minus y1 equals mx minus 1. So let's do that, right? I think that's probably the easiest way. So let's find out the slope of A first of all, right? There's a few ways of doing this. I'm just going to maybe do it the way I did it. Just give me a second there. Right, so let's look at the equation of M. It's 2x plus 3y plus 1 equals 0. We can find out the slope of that straight away, can't we? Because we know that the slope of that line is equal to minus A over B. Remember, way back, you can straight away, if the equation of the line is in the form of AX plus BY plus C, which it is in this case, we can work out the slope straight away. So in this case, we can say that the slope of M, subscript M there, right, is equal to minus 2 over 3. Now, we know, I'm going to call this line here S, right? There's probably a few ways to do this, but this is the way I did it. So I know the slope of S is perpendicular to M. So I know that that's multiplied minus 2 over 3 by minus 1. So if I multiply them together, so it's the inverse, so it's equal to 3 over 2. In other words, if you multiply 3 over 2 by minus 2 over 3, you get minus 1, okay? So that now we're building up something out here. Now we have the slope of S, and we also have a point on S, don't we? We have the point 2, 1, because this is the line. I'm just going to draw the line S right in red, so I'm clear. That's the line S, okay? We have a point on it, we have the slope. If you have a point and a slope, you can write the equation of the line. So then we can write down like this. Let's go back to black. Remember, y minus y1 equal to m into x minus x1. So in this case, it becomes the line of S, you can write down as y minus 1 equals slope, which is 3 over 2, times x plus 2. Working all that out, we can get that the slope, rewriting, I should say, S is equal to 3x minus 2y plus 8 equals 0. Okay, let's go back to the question I was asking for. Find the coordinates of B, the point on the line N closest to A as shown below. So S, we have the line equation of line S, we have the equation of line N, don't we? We have N, we have S, where they intersect is simultaneous equations. So I'll just write out here N is 2x plus 3y minus 51 equals 0. So we have S and N. And if we solve them by simultaneous equations, right? So it's multiplying this one by 3, multiplying this one by 2. And you get 9x minus 6y plus 24 equals 0. And the second one becomes 4x plus 6y. Cancel them. Minus 102 equals 0. 9 under that, you get 13x equals 78. And I'll just go over here. You get x is equal to 6, and then fitting back in for 6, you get y is equal to 13. So the point B, the coordinates of point B are 6, 13. Okay, so we solved for x, right? And basically what I did here, I didn't show it, right? But I would have just plugged x equals 6 into one of these formulas, right? The S here. So you put in 3 times 18 minus 2y plus 8 equals 0. You would have got 30. Okay, I'll just leave that there for a second for you. So again, this question could probably be done another way as well, right? But I don't think so. I think that's probably the most straightforward way. But again, you're using the fact that the most crucial fact in this equation was this, establishing that M of S, right? Because if M1, remember, if M1 is perpendicular to M2, right? Therefore, M1 multiplied by M2 equals -1. That's the important thing here. So we got the slope of M, and we knew that S was perpendicular to it because N and M are parallel. So S is perpendicular to N, it's also perpendicular to M, right? So by using that fact, we were then able to establish the equation of S. Once we had the equation of S, we already had the equation of N that was given to us. By simultaneous equations, you can work out where they cross, right? And we did, and that was the point B. So that was that one. I think that was a nice question, you know, that was a little bit of a tester, but again, if you understood slopes and, you know, some of your little formula that we did along, you'd have no problem with it. Okay. I think I have 2016 as well. I'll leave that there. Oh, yeah, should be okay now. I think I have 2016 too. Yes, this one. This is a 2016 paper too. So it says the points A, 6 minus 2, B, 5, 3, and C, minus 3, 4 are shown on the diagram. Find the equation of the line through B, which is perpendicular to AC. Okay, so let's draw it out. So again, what it's saying, find the equation of the line through B. So it's a line which is through B and is perpendicular to AC. Okay, I'll try and draw this here now nicely for you. So it's a line through B and it's perpendicular to AC. So it goes something like that. I'll try it again. That's not too bad, okay? So that's the line, right? Because that's perpendicular there. So it's a line which is through B, yeah, and it's perpendicular to AC. So that's our line, okay? Find the equation of the line. Right, what do we know? We know that it's perpendicular to AC. So if we follow this, if we found the slope of AC, then we'd have the slope, wouldn't we? We'd have the slope, and then we'd have a point because we have the point B. So we have the slope, we have the point, therefore we can get the equation. So A. Well, we're trying to find the slope of B, right? or so what are we calling it? Find the equation line, whatever we're calling, doesn't matter. So we need to find out the slope of AC because our slope of our red line there is perpendicular to it. So the slope of AC is using, y2 minus y1 over x2 minus x1. So in our case here, y2 is minus, let me see, it's 4. It's A and C, where we're looking at A and C. So it's 4 minus 2 minus 2. All over minus 3 minus 6, x2 and x1. Right? So that's equal to, works out at minus 2 over 3. Now, the line that we're looking for, perpendicular to MAC, so the slope perpendicular to MAC is equal to, obviously, invert it, 3 over 2, and get rid of the sign, is 3 over 2. So we have the slope of the red line, and we also have a point. So using this, the usual equation, y minus y1 is equal to m into x. Okay, so we call it L1, right? Call it L1. So L1, plugging in the values, is y minus y1, which is 3, and m is 3 over 2, into x minus x1, which is 5, isn't it? 5, yeah. So bringing the 2 across and leaving the 3 there, working that out, you get 2y minus 6 is equal to 3x minus 15. And writing that out nicely, you get that L1 is 3x minus 2y minus 9 equals 0. That's the answer to part A. Okay, not too difficult, I think. But again, the important thing here was establishing the slope of one line and getting the slope of the line that's perpendicular to it, which again is the M1. I'll write it down here. So look, it's M1 multiplied by M2 equals minus 1 if M1 is perpendicular to M2. That's the important thing to know in this question. Okay. Part B is use your answer to part A above to find the coordinates of the orthocenter of the triangle ABC. Again, there's a kind of trying to trick you here a bit, right? But it says use your answer, right? So what it is saying then, use your answer to find the coordinates of the orthocenter of the triangle ABC, the orthocenter. So let's pick, what I did here is I picked one of the other lines, right? So I picked, so that was the first part here was through B, right? Perpendicular to AC. What if we took a line through A that's perpendicular to BC? So through A, so I think I'll draw this out, and it's perpendicular to BC. So BC, let's just do that out like that. So through A, perpendicular to BC, well then you're going to end up with something like that. That's perpendicular to that, isn't it? And it's through this point here. So I did this, the last one was for point B. This one I'm just doing it for point A, right? I could similarly do it for point C. So let's look at point C. Let's do that in a, no, the chances of me ending up in the right place are strange, right? So we go through C and it's perpendicular. I'll do this in blue. And actually, so let's extend B, right? So let's go perpendicular to that through C. So I have to try and hit that somehow. Not bad. Okay. So what we've done there, right? We've gone through C, we've gone through A here, right? And they're perpendicular to the opposite side. And then we end up here with what we're looking for. That's the orthocenter, right? So again, it was like using what you did in part one, just applying it, right? So I didn't have to do C there, I only had to do one, right? So now I'll write it on this actually, if it works. I don't know if it will work or not. So that's part A down there, right? So part B here, right? So again, let's do the exact same thing. The last time we picked MAC, this time I'm picking MAB, right? So MAB is equal to y2 minus y1, I get same thing again, right? So in this case, it's 3 minus 2 all over 5 minus 6. So what I'm doing here is look, it's the slope of AB. So that line here, right? So that's the slope of AB is equal to -5. So this perpendicular slope to AB is obviously inverted and put in the minus 1/5. Again, what have we got now? We have the slope of the line, the blue line. That's what we're doing here now, is the blue line, right? So we have the slope of the blue line, which is 1/5. And we have a point on the blue line, don't we? Which is the point A. So let's call that L2. Can I call that L2? Sorry, I'm doing it different. I'm doing the purple line. Sorry, yes, it's the purple line we're going to do. Sorry. So we have what we did there, first of all, is we got the dotted line here, the dotted purple line from A through B, right? We got MAB, and we got this, the line that's perpendicular to it, which is actually the purple line there, right? So my apologies. And we call that L2. L2. So therefore, the equation of L2, this again, it's y minus, I'll write it out. Y minus y1 equals m into x minus x1. Correct? So in this case, it's y minus y1, which is 4. And the slope is a fifth to x minus 3. Because the point I picked here was C, right? Because you know that the line goes through C. Working all that out, then you get L2 is equal to x minus 5y plus 23 equals 0. So we have L1, we have L2. Guess what? Simultaneous equations. Let's write them out. So it's L1 is 3x minus 2y minus 9 equals 0. And L2 is x minus 5y plus 23 equals 0. What I did is the different way I just then said that look, x is equal to 5y minus 23, isn't it? I just put everything off the other side, and then I just fill that in to L. I put L2 into L1, and I got 3 times 5y minus 23 minus 2y minus 9 equals 0. And then working all that out, right? I can write out it, why not? We have a bit of time. 15y minus 69 minus 2y minus 9 equals 0. 13y is equal to 78. And y is equal to 6. And then substituting that backing up over here. So x is equal to 5 times 6 minus 23. So x is equal to 7. So your answer then is that point, we call it 0, right? The point coordinate of 0 is 7, 6. That's your answer.
Thank you, Mark, for a great presentation. And there was lots of examples. And for sure, the main thing with this is to be able to understand it. And then you can apply it to any problem. And that's that's the real useful tool. Then you've got, you can apply it to different things. Don't forget, inside in your log tables, there are a lot of formula and things that you don't have to remember stuff, but you do need to know how to use it, and that's the practice. All is left for me to do so is say thank you once again, Mark, for a great presentation, and
welcome
to the students. Hopefully we'll see you here next week for the geometry of the circle tutorial with Deirdre de Valish. Okay, bye for now.